Welcome everyone. In this short video I'm going to talk about this 8-digit 7-segment digital display. So this is a very nice display because it's relatively simple, relatively small, and it's very easy to write software for it to show the numbers that we want to see. And the reason why I made this video is because I want to use this display in several projects, and I could not find any good resources on printing floating point numbers on this display. Most of the tutorials and other resources I saw was only printing numbers, but they did not really process like realistic numbers like floating point numbers, which can come from a voltage measurement, a weight measurement, or resistance measurement, and so on and so on. So in this video I will cover those topics, and I will show you how to properly process these numbers and then print them on this display. And this display is driven by a MAX 7219 display driver, and that driver basically switches in between these 8 segments, and then it can switch on the 7+1 independent LEDs within these digits, and then it shows the numbers. And this display is mainly for showing numbers, but you can make up some simple characters such as the letter L, A, H, and so on, whatever that you can fit in on this display style. So as I said, we have 8 digits, and each digit has 7 segments for the number, and each let's say cell has its decimal point. And in my tutorial, what I did, I decided right before coding everything that I always want to see 2 decimal digits. So there will be 2 numbers on this side of the display, which will be the 10th and the 100th. And then about that, the 6 other digits will be any kind of positive number. I have to emphasize that in this tutorial, I will show you the positive numbers, because mostly we measure positive numbers. If you measure weight, that will be positive. If you measure voltage with the proper polarity, it will be positive. Resistance can only be positive, and so on and so on. So we will cover only positive numbers, but if you follow this tutorial carefully, you will have the knowledge to, let's say, add a few lines to the code and make it possible to read, process, and display negative numbers. So the display communicates with an Arduino Nano, and it does it through a SPI communication protocol. And since the whole circuit only works with the SPI protocol, I will not publish any kind of schematics or drawings, because it's not necessary. We have 3 SPI numbers: D in, chip select, and clock. Those are the normal SPI numbers or pins, 12, 13, and 10. You will see it in the code. And then it's fed by +5 volts. And of course, the ground is also connected to the board. So it's a very simple connection. And due to the fact that we have SPI, we can have multiple of these displays at the same time. We just have to activate the chip select for the given display or segment, and then we can communicate with it. So all I have to do, I have to plug this in, and I will tell you what is happening on the display. So just a mobile phone charger, and then you can start to see some numbers. And what you see, you will see 10 or now just 7 more floating point numbers. So we have 6 digits, and based on the random number generation, there will be a few digits here. And then there is a decimal point here after this digit, and we have the tenths and the hundredths. And as you can see, sometimes we have 5 digits, sometimes we have 4 digits, and so on, based on the mood of the random number generator. And now this is the, let's say, other part of the demonstration that I want to show you. As you can see, there's a very fast counter here. I just have a counter which counts up by 10 every 10 milliseconds, and we store that value. So every 10 milliseconds we increase the value by 10, and we print it here. So this is almost like a second based counter. So you can see that 27, 28, 29, so these digits change almost every 1 second. And this counter is also using some practices or let's say different exercises which allow us to properly print the numbers on this display. And this is basically the whole demonstration. But once we go through the code, you will see that this display can be used in a lot of projects, and it is a quite powerful display. So now I want to move to my computer and continue with the code, because the more interesting part is in the coding part. So we have arrived to the computer, and now we will be looking at the code, and I will show you line by line how the code works. And at the end of this tutorial, you should be able to customize this code up to your requirements. So what we have here, I am using the LedControl library. So it's a little bit of cheating, but this library allows us to at least print the numbers by segments, and then we have to do the rest of the task still, but this eases up our work. So here we just have to create this guy here. We call it LC, following the tutorial, which you can find on the website of this LedControl library. And we have the SPI pins defined, and basically that's all. And I'm using the native SPI pins, so there is nothing extraordinary happening here. And now, opposing to my general practice, I define most of the variables runtime inside the code, inside the functions. And here I just use a few variables for the timer and the counter. So you will see the rest of the variables later. But what this timer does is just helps us to count the elapsed time, which is basically following the counting up inside the main loop. And then the counter, that's just the counter which we increase by 10 every 10 milliseconds. So then in the setup, I have a serial initiated because I used it to debug everything, and I kept everything in the code. So you will see how this code works when you look at the code itself. So then again, this is basically the same coding sequence that you can find in the original code for this library. So we start the display. I set up a relatively low brightness, but it's more than the lowest. So the lowest setting is either 1 or 0, I don't remember. But this is like a, let's say, medium-low brightness. And then if there is any garbage on the display, I clear it. And here, this code makes sure that in the beginning, so in the setup part, we have 10 different floating point numbers printed on the display. So we run this float to decimal number 10 times with 3 seconds of delay between each other, so we have the time to check the numbers. And basically this function, which is the core of this demonstration or tutorial, and let's jump to that and let's see how it works. So I put a lot of comments here, so if you don't want to follow this video, just go to my website, link is in the description, and just check the code, because you will see everything, a lot of comments, a lot of examples and calculations. So what we can see here is we have a floating point number, and this is now 0. I kept this line here about it because I just wanted to have something which I write down. But then I said, okay, I should generate my own random floating point number. So we just create this variable, and then we pass a value to it. And how we do our random floating point number is that we generate a random number now with 5 digits, but actually this can be 6 digits. So this will be a random integer, which is basically can be something like this. And then this part what it does is it generates a number between 0 and 99, and it divides it by 100. So that number will be something between 0 and 0.99. So then the final number will look something like this. And then, as a checking, I just print this random floating point number. And now we have to start processing this number, because you cannot just pass this floating point number to the library and ask it to print. So we have to separate it into, let's say, integer and decimal part. So we have to check what is to the left side of the decimal point and what is to the right side of the decimal point, and then print everything individually, plus put the decimal point to the right place. So what I do here is that I cast the floating point number into a long type, which means that this casting will cut off the decimal numbers, and we will be left with a simple integer. So we get the numbers which are to the left of the decimal point. And I put an example here how it will behave. Then I want to check this number, so again I just print it on the serial port. So far so good. Then I did one type of calculation for the decimal part. It works, but maybe there can be a more, I don't know, intelligent or elegant alternative for this. So one way to get the decimal part is something like this. So we take the floating point number and multiply it by 100. So we shift it by 2 decimal digits towards the left. So that converts our tenths and hundredths to basically decimals. And we cast it into long, and then this number, which is in now long, is, let's say, divided. This is the modulo operator, divided by 100. So it's not divided by 100, but it's moduloed by 100. And that will give us the decimal part. But instead of that, we can do another, I think, more nice thing, is that we take the original floating point number, and we know already the integer part. So we do this subtraction, and then the result will be something like here in this example, let's say 0.74. And then we multiply this number by 100, as you can see it here. So then that number becomes 74, and that is our decimal part. So the numbers which are located to the right of the decimal point, tenths and hundredths, here and here. But then there is a slight issue here. If you use float, then there is usually some garbage after your numbers that you cannot see. So for example, if I show this kind of number or highlight this kind of number, you can see that, for example, we have this number, let's say a manually typed number or a random generated number, which is shown as this, 87,073.37, but inside the memory of the computer that may be represented something as something like this. So 87,073.36, 50, 21, 21, 25, and so on and so on. Which is also, if you round it up to the hundredths, is 87,073.37. But then the issue is that then if you just cut these two numbers, the computer will see 36. So sometimes you can have a plus minus 0.01 error in this. So if you don't like this, you have to round manually your number to the last 2 digits, and then do this part. But yeah, it works, and plus minus 0.01 for me, it's not a big problem. And I'm aware of this thing, so if I want to, I can correct it. So then again we check the things and we print the decimal part. So now at this point we can see it on the serial terminal that we managed to recognize the numbers properly. And I can assure you that it works properly. And then now we know also, I wrote it down here, that we want to keep 2 decimal digits, and it will be always 2 digits, so that's like manually and forcefully set. And then we also know that based on this, we have 8 digits total on the display, so 6 digits can be used for the integer part. And we know that we have some kind of floating point number, but we don't know the number of digits. So what we do here, we create a counter which just stores the number of digits for the integer part. And then I created like 2 temporary, I call them temporary variables, which also store the value of the integer part. And they will be used by different parts of the code. And since I did not want to modify the original variable, then I decided to just copy them into some other variables. So first, in this part, we just keep dividing the integer part, the temporary integer part, by 10. And as long as we can do it, so we still have like remainder in this operation, we can increase the integer digits by 1 in each iteration of this while loop. So what happens here is that we have the original floating point number, which we process somewhere up in the code, somewhere here. And then we take the integer part of it, and that integer part is copied into this TMP integer part variable. And then we keep dividing it by 10 here. So what happens is that this number is divided by 10, so it becomes this, and then again we do a division, becomes like this, do a division, becomes like this, we do a division, becomes like this. So this is 1, 2, 3, 4, 5 divisions, and in fact this number is 5 digits. So at the end of this while loop, when we can, or the code can escape this while loop, the value of the integer digits variable will be 5, which coincides with the number of digits here. And then now we can create another variable, which I just call digits position. And what that does is basically determines the number of digits in the whole number, because we know that we always have 2 digits because of the decimal part of the number, but we never know the integer part in before. So if it's 3 digits, then this value becomes 5. If it's 1 digit, this becomes 3, and so on and so on. But this plus 2 is always there because we force this thing to be 2 digits always. And then I just deleted a line here, which was there from an earlier trial. And then we print this if we see the number of digits properly. So we know everything, and we can start to do some fancier things. So what now we have to do is that we have to store each individual digit in an array. And why we do it like that? Because we can imagine the display also as an array, and each segment of this display, or let's say each number of this display, can be imagined as an element in the array. And then it's very easy and smooth to fill in the digits when we read the floating point number using a for loop or a while loop. And also it's very easy to print the numbers using a for loop. And I will do it like that, so you will show it how it's done. So what we have here is there is an array, which I call digits, which has the size of this digits position. So we previously calculated the size, and that is the size of the digits. We also know that the decimal digits, so the number of decimal digits is 2. And then I need a temporary variable for the decimal part. So we just copy the decimal part into this because we will process it several times and I don't want to lose the original value. So first I take care of the decimal part, and I do it manually because it's just a few lines, so I did not want to mess up everything with the for or while loops. So what I do, I know that I want to put the decimal part, the second decimal digit here into the integer digits +1 place. And what it means that we have, for example, this line, and we want to, let's say, extract this number from it. So this is the last number, basically. And why the +1 is because the integer digits starts counting from 0, so the 0 element is also there. And then this will be represented when you call this number. And when you call the number, which equals to the integer digits, that will give us the tens. And that is this number, the 2. And we also store it in this. So now what we can think about is that how we print on the display. So the display is sort of filled up from the right to the left because we have the hundreds, the tens, and then the ones and the tens and hundreds and thousands and so on and so on. So then if we look at the number and as we read it as a human, then we see that this is 634.23. But then when we fill up the array, starting from the 0th position of the array, then we read it from right to left. So 634.23. So that's how it works. And now I hope that you can understand this part more. So basically, when we have the integer digits +1, that means that we are here. And then when we have the integer digits, then we are here. And then we have integer digits -1, -2, and -3. And this is not +2, while you can see this like physically as 2 digits, but it's +1 is, once again, it's because we start counting from 0 and not from 1. And then again I check the digits, print it on the serial port, and I made sure that everything is fine. And also I just print the integer digits. And this part is the same exercise that we did with the decimal part, but we have more digits here, or preferably we have more digits in the integer part, maximum 6. So we just keep filling up the rest of the array. And then I just print a separator, and to check the contents of the array, I print the array. So we will see all the elements. And I will show you in the serial terminal how this works. And then finally, after this, we are sure that, okay, we have the correct numbers in the array. So we clean up the display. And then in this for loop, what I do, I know that I want to have a decimal point at the second, let's say, segment, or more precisely in the third segment. So then if j equals 2 in this for loop, then inside this set digit place or function, I set the last argument to true, which also means that the code will know that it should put a decimal point there. And what's the rest of this argument is that this is the address of the display. So if you have multiple displays, you can address them here. And then the j is just the running index of this for loop. And then this is the value. And what I do here is that I take the array, the digits array, and then I know the digits position, which is the total number of digits in the whole number. So then I subtract the j, which is again the index of this for loop, -1. And the -1 is because when we count the digits, we say that first, second, third, and so on and so on. But when the computer counts the elements in the array, it says that 0th, first, second, third, and so on and so on. So we have to put a -1, otherwise the code will run out of the array and it will throw an error. So this happens only in the j equals 2 case, but in any other cases, we do this. We do exactly the same, but we just don't print the point in each cell. And I took an example with the previous number that I showed up here, and I manually wrote down everything, so you can check it yourself. But what happens here is that when j equals 0, we call the fourth element of this array, which is like physically the fifth number in this storage in the array, and that will get us the last digit, so the 3. And then we go to the digits 3, which is the fourth element physically, or the first element when we check the display from the right to left, and that will give us the 2, and so on and so on. So you can see how this works. So once again, we have a floating point number, we separate it into an integer part, a decimal part, then we have to count the number of digits in the integer part, and then we have to create an array with the correct number of elements, and then we fill up this array with the numbers, and then we call these elements of the array and print them on the display, and this is how it works. And once again, this works with positive numbers only in this kind of tutorial. And then you could see it in the other type of demonstration that after I printed some floating point numbers on the display, it all of a sudden started to count up very fast. And that thing is realized in this count up function. And again, this is quite similar to the previous way of thinking, but we don't have to take care of the floating point numbers here. So all we do is we just have a integer number, and then we work with that. So we know that we have to store the number of digits, and then I have two, let's say, temporary variables which store the copy of the value of the counter. And how the counter looks like is that we have the counter which is running in the loop. So here, in each iteration, we increase the value of the counter by 1. And then what we do here is that we just multiply it by 10. So we count like 0, 10, 20, 30, 40, so on and so on. And immediately I made a copy of this because I want to use this value later in the code as well. So again, similarly as in the previous exercise up here, we have to count the number of digits because we have to know how to place the numbers on the display. And then I create a copy of this number of digits, and I create the array with the corresponding size, so the correct number of elements, which corresponds to the number of digits which we just counted up here. And then until we count to the number of digits, we fill up the array with the corresponding numbers. So the tens, with the ones, tens, hundreds, thousands, and so on and so on. And once we are done with this while, we clear the display, and previously shown here, we do the same. So we run this for loop until the number of digits, and we keep putting on the numbers, basically from right to left on the display. And this is how it works. So this is like the very fast counter which I showed you in the physical demonstration. And now I'm going to connect my Arduino, and we will see how the serial terminal looks like. So how you can troubleshoot your code and so on and so on. So this is how it looks. We print the random float, and we extract the integer part, and then we extract the decimal part. And here you can see the difference between the, let's say, rounding. So this can happen. And then we know the number of total digits, and that is 1, 2, 3, 4, 5, 6, 7. So this is again correct. We know the 0th place of the decimal, and that is 3. And the first, that is 3. Since they are identical, it's not really easy to see if they are correct. But based on this example down here, I can say that this is correct. Because the 0th place, this should be again 3. That is here. And then the first place is here. And then we count the integer digits, and that's 5. So that's correct again. And here in this part, we just check if the array was filled up properly. And you can see that we have 16807, 16807, and then 3, 3, and 3, 3. So this is correct. And if you see down here, we just have 10 more numbers as examples. So we can look at another example, and this is good because this shows the proper numbers. So this is 72,675.17. And then you can see that the integer part is captured properly. And now we don't have the rounding error. So the 17 is 17. Total number of digits is 7, 5 plus 2. And we see that the decimal 0, so the last digit is 7, and decimal 1, so the last -1 digit, is 1. So this is correct again, and integer digits is 5. That's not a rocket science, as you can see. And again, we have the correct numbers. 7, 2, 6, 7, 5. That's here. 1, 7, 1, 7. So this is correct again. And then, as you can see, it works really nice. So basically this was the whole tutorial. If you want to see more details, go to my website, curiousscientist.tech, and I also put the link in the description, so you can find everything there, all the resources. Please don't forget to subscribe to my channel, that helps me a lot. And I hope that this video was useful and interesting for you. I hope you learned something, and see you in the next video.